Okay. In the previous chapter, chapter 11, we have covered the fundamental theorem of arithmetic, and then we have also covered some theorems on the prime factorization. Okay, and now we are going to talk more about the prime numbers. So, as you are probably beginning to appreciate, the prime numbers are fundamental to our understanding of the integers. So in this chapter, we will discuss a few basic results concerning the prime numbers and also hint at vast area of questions, some solved, some unsolved, in current research into prime numbers. The first few primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and so on. Now it is quite simple to carry on long way with this list, particularly if you have a computer at hand. How would you do this? The easiest way is probably to test each successive integer n for primality by checking for each prime p less than or equal to under root n, where p divides n. So the question would be, how would you write more primes in the list? So if you have computer, then the easiest way is to probably test successive integers. The easiest way is probably to test each successive integer n for primality, and that we can check for each prime p less than or equal to under root n, whether p divides n, and such primes p will of course be in your list, right? If none of these prime p divides n, then n is prime. And if these prime p P is prime. And some more sophisticated methods for primality testing will be discussed in the chapter 14. Now, probably the first and the most basic question is to ask, does this list ever stop? Does this list of primes ever stop? This was also a question. This is also a question. Okay. Now, in other words, is there a largest prime number? Is there a largest prime number? Or does the list or does the list of primes go on forever? The answer is provided by the following famous theorem of Euclid. So for all these questions, the answer is provided by this theorem. 12.1 given by Euclid, 300 BC. Thus says there are infinitely many prime numbers. Right? And we'll try to prove this. So if you see these questions ask where does this list of primes ever stop, or is there a largest prime number so that we can stop the list, or does the list of primes go on forever? And the answer is that the prime numbers are infinite, so you cannot find a largest prime number, and this list goes on. So if you write an answers, so does the list of primes ever stop? The answer is no for this one. Is there a largest prime number? The answer is no. Does the list of primes go on forever? The answer is yes. Okay, so let's prove this theorem. So this one is the classic proofs by contradiction. So by contradiction, assume the result is false. Result is false. That is, there are only finitely many primes. This means that we can make a finite list of primes. So that is 1, P1, P2, dash dash up to Pn. Of all prime numbers. Now define a positive integer. and then we can write its prime factorization. It's the product of P1, P2, P3 up to Pn plus 1. So this is the product, and then we are adding 1. Okay. Then we have a proposition. So by proposition 8.1, n is equal to product of primes, a product of primes, say, and can be written as q1 dot dot qr with all qi primes is q1 is prime. It belongs to the above list of all the primes. Right? So q1 is pi for some I. Okay. Now we say that q1 divides n, and hence pi divides n. Also, pi divides the product p1, p2 up to pn. And this implies, which is equal to n minus 1. So, yeah, which is equal to this product of primes p1, p2 up to pn is equal to n minus 1. Thus, pi divides n and n minus 1. But this implies that pi divides the difference between these numbers, which is namely 1. Okay. Perfect. But this is a contradiction. That means P is not prime. This is a contradiction. Hence, we have infinite primes. So this proof says that we have infinite primes. Okay. Now, theorem 12.1 is, of course, not the end of the story about the primes. It is really the beginning. A natural question is to ask that follows from the theorem is, what proportion of all positive integers are prime. Okay. On the face of it, this question makes no sense. Like, we know we don't know all the positive integers. So how can you find a proportion of them to be prime? As the integers and the primes both infinite sets. So you can say this question makes no sense. Is the integers and primes are both infinite sets, right? But one can make a sensible question by asking. So let's ask a sensible question, which is, given a positive integer n, how many of the numbers 1, 2, 3, so on to n are primes? So let's say we have a positive integer and any positive integer. And now you want to find that from 1 to n, how many of the numbers are prime? This is a sensible question. Okay. Now, is there any reason to expect to be able to answer this question? On the face of it, no. If you stare at a long list of primes, you will see that the sequence is very irregular and it is very difficult to see any pattern at all in it. So, like, write 1,000 primes using any computer, and then if you look at it, you will not find any regular pattern, and you will not find a pattern to follow or a general formula to follow that to find the primes. It's very hard. Now, why on earth should there be a nice formula for the number of primes up to n? So the comment would be, why on earth should there be a nice formula for the numbers number of primes up to n? Okay. The amazing thing is that there is such a formula. Wow. There is such a formula, albeit an asymptotic one. I will explain this word later. The great Gauss, by calculating a lot with list of primes and also having a lot of built-in thoughts, formed the incredible conjecture, informed guess, conjecture is an informed guess that the number of primes, or you can say educated guess, number of primes up to n should be pretty close to the formula. So you can write the great Gauss formed an incredible conjecture that the number of primes up to n should be pretty close to the formula. And formula is n over log at base e of n. Now to understand this a little, compare the number of primes up to 10 power 6. To understand, this, compare the number of primes up to 10 power 6, namely your 7, 8, 4, 9, 8. With the value of 10 power 6 over log e 10 power 6, namely so now this number will be equals to closely 7 to 3, 8, 2.4. Okay. Difference between these two numbers about 6,000. The difference between these two numbers is 6,000 and appears to be quite large, which is quite large, but their ratio is 1.085, quite close to 1. Quite close to 1. Okay. But it was on the ratio rather than the difference that Gauss concentrated his mind. So you can say Gauss concentrated on ratio rather than difference. Okay. And his conjecture was the ratio of the number of primes up to n, and the expression should get closer to closer and closer to 1 is and gets larger and larger. So you can say the conjecture by Gauss is that the ratio of the number of primes up to n and the expression n over log e of n should get closer and closer to 1 is and gets larger and larger. Right? Formally, this ratio tends to 1 as n tends to infinity. You can say that limit n tends to infinity n over log e of n is 1. Okay. Now, Gauss did not actually manage to prove his conjecture. The world had to wait until 1896 when a Frenchman, Hadamard, and Belgian de la Vallée Poisson both produced proofs of what is known as the prime number theorem. So let's give that theorem. So we have theorem 12.2 given by Hadamard and de la Vallée Poisson. Given by these two in 1896. This is a French mathematician, and then this is Belgian mathematician. They give this theorem, and the statement is for a positive integer n, let pi of n be the number of primes up to n, then the ratio of pi of n and the expression n over log e over n tends to 1 is, I think I should write something. This ratio where we have mentioned pi of n is the number of primes. Okay. Tends to one is n tends to infinity. Okay. I.e. the ratio can be made is close is we like to 1 provided n is large enough. Okay, perfect. Now the proof of this result uses some quite sophisticated tools of analysis. Nevertheless, if you are lucky, you might get the chance to see a proof in an undergraduate course later in your studies. In other words, it is not that difficult. You may get the chance to see it. This is an introductory course, so there's no need to prove it. You should not think that every question about the primes can be answered, not by you, then by some expert or other. On the contrary, many basic questions about the primes are unsolved to this day, despite being despite being so not all the questions are solved about the primes or answered about the primes, and many basic questions about the primes are unsolved to this day, despite being studied for many years. Now let's finish this chapter by mentioning a couple of most famous such problems. So let's mention that. So there is this problem called the Goldbach conjecture. This conjecture says if you do some calculations or program your computer on your computer, you will find that any reasonably small even positive integer greater than 2 can be expressed as sum of two primes. So any reasonably small even positive integer greater than 2 can be expressed is a sum of two primes. Now let's see an example. So let's say we have 10, that is 7 plus 3, both are primes. Let's say we have 50, that is 43 plus 7. Okay. Let's say we have 100, that is 97 plus 3. Let's say we have 8,000, and that is sum of 3943 plus 4057, and so on. Based on this evidence, it seems reasonable to conjecture that every even positive integer is the sum of two primes. This is Goldbach conjecture, and it is unsolved to this day. Other one, the other one is the twin prime conjecture. This says if P and P plus 2 are both primes, prime numbers, we call them twin primes. For example, we have 3, 5, we have 5, 7, we have 7, 13, we have 71, 73, we have 1997, 1999. If you stare at a list of prime numbers, you will find many prime pairs of twin primes getting larger and larger. One feels that there should be infinitely many twin primes. And indeed, that statement is known as the twin prime conjecture. Can one prove the twin prime conjecture using a proof like Euclid's in the Theorem 12.1? Unfortunately not. Indeed, no one has come up with any sort of proof, and the conjecture remains unsolved to this day. So this was a very nice chapter on the prime numbers. More on prime numbers. We have talked some of the properties of the prime numbers, and then we have given that there are infinitely many prime numbers, and this is the famous theorem of Euclid given in 300 BC. And then we have some interesting number conjectures given by Gauss, and then proved by Hammered, De La Ville, Poisson in 1896 that indeed Gauss was true. And then we have some good Goldbach conjectures, and then the twin prime conjecture. Okay. Thank you so much. Bye. Please do subscribe and follow.